Alright. Well, hi. This is Mr. Mitchell, and clearly I'm not in my classroom. I'm in the safety of my own home as I discuss with you this section of the Physics C notes. I was going to record this before I left school today, but I was way too tired. I literally, there's a recording of this where I'm literally like falling asleep as I'm doing this, and I was like, I need to go home because this is ridiculous. I need to take a nap and I can do this, alright? Okay, so here I am, right? Kirchhoff's law, solving problems. I have a much nicer document camera and a much nicer face cam at home than I do at school, so you're going to get some HD stuff here. Okay, alright. Well, we are going to start with this problem right here. Battery epsilon is connected to 3 series resistors R1, 2, and 3. Okay, rank the 3 resistors based on which one has the greatest current through it. Put equal signs between those that have the same current and greater than signs between those with unequal currents. Okay, so first and foremost, right, we're going to look at your resistors, okay, and your resistors are all in series, okay. It's asking about current, and you should know that everything that's in series with each other has the same current. So all the resistors are in series with each other, therefore they should all have the same current going through. Okay, R2, R3, okay? Why is that? It's because all resistors are in series with each other. Okay, so therefore they all have the same current, right? I think you can kind of draw that conclusion from there, but that's perfectly fine. Now we're ranking them based on voltage drop. Okay, let me move this thingy down a little bit so I get myself a little bit more screen real estate. Okay, now we're going to talk about voltage drop. Okay, voltage drop. Which one has the greatest voltage drop across it? Well, we know that I'm going to refer to this as the pyramid of knowledge. Okay, I'm going to call upon the pyramid of knowledge. Okay, that's the pyramid of knowledge, right? And you know that if you can multiply across here and then divide here and divide here, okay, to figure out, you know, you just cover what you're looking for. You cover what you're looking for, and then it tells you what the formula is going to look like. So we're looking for voltage, right? Okay, V equals IR. Okay, so if you know that current is going to be the same in every single resistor, then there's only one thing that voltage is dependent on, and that is resistance. Okay, so the greater the resistance, the greater the voltage through it, right? So that means R3 would have the greatest voltage, and then R1, and then R2, okay? And why is because by V equals IR, if I is constant, then more resistance equals more voltage, okay? Very straightforward, right? Okay. This next part is basically what we kind of want to get at is figuring out voltage drop and current through each resistor. Okay, kind of one of the main points of this lesson is being able to properly solve circuits, and this is the first major step to doing that. Okay, so determine voltage drop and current through each resistor. Well, right, we've already established that the current is going to be the same for every single resistor. Okay, let me just write off to the side here, just some reminders is what each resistor we're talking about, right? This is 3 ohms, this is 2 ohms, and then this is the 5 ohm resistor, okay? So just to kind of remind myself which each of these resistors are, okay? Okay, going back up to the circuit, we can do a couple things here. First off, let's get the equivalent resistance, right? It's really easy because they're all in series. So the equivalent resistance is just going to be equal to 3 ohms plus 2 ohms plus 5 ohms, okay? And that should give you 10 ohms, okay? Now, we know the EMF of the battery, we know the equivalent resistance, therefore we can figure out the current through the battery, which is what we want to get, right? I'm calling upon the pyramid of wisdom again, or the pyramid of knowledge, okay? We're looking for V over R. Well, it doesn't take a rocket scientist to figure out 60 divided by 10 is going to give you 6 amps. Okay, this is bad. Okay, so when we are doing right here, right, our current is 6 amps through the battery, and the battery is in series with every resistor. So therefore, the current through each resistor is going to be 6 amps as well. 6 amps, 6 amps, 6 amps. Okay. Okay. Now, what we're going to do is we can figure out the voltage drop, right? Well, calling upon the pyramid of wisdom or knowledge, right? Cover up the V. It's just I times R. 6 times 3 is 18. Okay, 18 volts. And then 6 times 2 is 12 volts. And then 6 times 5 is 30 volts. Okay, that's all you have to do for that. And then finally the power, right? You remember that power is equal to I times V. Okay, all you gotta do is multiply current and voltage drop. 6 times 18 gives you 108. Okay, 6 times 12 gives you 72. Okay, and 6 times 30 gives you 180. Okay. Okay, now what we're going to do is we're going to fill in this this electric potential graph. And if you haven't seen how to do one of these yet, it's pretty simple, right? We're just graphing the electric potential or the voltage for a charge as it moves around the loop. So it starts out at the battery, right? And it goes through resistors in order 3, 2, 1, okay? So starting out, it should have 0 voltage at the very start, but when it goes through the battery, it's going to jump up to 60, right? Okay. So it jumps up to 60, it'll stay 60 for a minute, and then it's going to go through R3, and when it goes through R3, we're going to lose some of the volts, okay? So we're going to lose a couple of volts here, I think, and so in R3, we have a voltage drop of 30, which means we're going to lose 30 volts here. So we're going from 60 down to 30, so this is 40, 30, okay. 50, 40, 30, there we go. Okay, and then we stay at 30 for a minute. We get to R2, we're going to lose 12 more volts, okay? And we're going to be left probably about right here-ish. It's not perfect, it's probably not going to be perfect, okay? And then at R1, it's going to take our remaining 18 volts, which will give us back down to 0 volts. Now, when you create one of these potential graphs, okay, the most important thing is to make sure that everything adds up properly, right? So right here on the left, this should, we gain 60 volts, okay? Then we lose 30, okay? And then we lose 12. And then we lose the remaining 18 that we had, okay? So you want to make sure it adds up properly. When you do one of these graphs, right, it should always start at 0 and end at 0, okay? And then you should never regain any energy unless you are going through a battery, okay? Which, again, is very particular cases, okay? The voltmeter, right, if you want to measure the voltage across the battery, okay, to measure the voltage of the battery, all you would need to do is to make a parallel connection to it. So we could do something like right here to right here, boom. Okay, and then to get the ammeter that can measure across R2, we need to put it in series with R2, but we don't want to put it in front or behind any other resistors. So we can just slide it right there. Okay, there's the ammeter. You could put it on the other side if you wanted to as well. Doesn't really matter. Okay. All right, that's that first one. So let's move on. Okay. 3 resistors now. This time, instead, it is now in parallel. Okay, so we take our resistors and we put them in parallel. First and foremost, rank the 3 resistors based on which one has the greatest voltage drop across it. Okay, so we're looking for the greatest voltage. Okay. If we, well, this is in parallel, right? So by the parallel rule, the voltage across everything in parallel is the same. Well, everything's in parallel here. Battery's in parallel with R1, which is in parallel with R2, which is in parallel with R3. So, therefore, everything should have the same voltage across it, right? V1, V2, V3, okay? Should be the same, because all voltages are same in parallel. Okay. So when you're in parallel, all voltages are the same. Okay. Now, the current isn't going to be the same, right? And that's why I'm calling upon our pyramid of knowledge. Okay. That's not a very good color to use here. We'll use this other one. Okay. And we've got your VIR. Okay. Still not a super great color. Let's change that out for green. Okay. Okay, so we got V and then IR, right? We're looking for which one has the greatest current through it. Well, you notice that current is dependent upon voltage and resistance. So the greatest current, if voltage is the same, right? The greatest current is going to flow through the resistor with the least resistance. And in this case, that's R2. Okay. Then it goes to R1, and then it goes R3. Okay, so the one with the most resistance would have the least current. And why is that? Because, again, by V equals IR, okay, if V is constant, then more R equals less I, okay? Focus it a little bit. I'm kind of losing focus here. Okay. Determine the voltage drop across and current through each resistor. Okay, so we're doing the same thing as we did before. Okay, we're going to figure out the voltage drop across and the current through each resistor. Okay, now it's a little bit easier for us now because we can actually get the voltage right away. And the reason that works out is because, let me just write our resistances right here, 3 ohms, 2 ohms, and then 5 ohms. Okay. The reason that this is a little bit easier is because what's happening is our voltage should be the same for every element, right? Our EMF has already been given to us as being 60. So this means that we've got the same voltage here, 60 volts, 60 volts, 60 volts, okay? And it makes sense because, again, remember, you don't want any charges coming back to the battery with any energy. It needs to get rid of all of its energy, okay? So if it can only pick one of these branches, out of all of them, then it will have to give all of its energy to that one resistor in there. So each resistor here has a voltage drop of 60 volts, okay? And that actually allows us to just straight up Ohm's law of the current here, which is easier than doing a bunch of other random steps, right? So it's actually a lot easier to just go ahead and do the current here. Current is equal to V over R, right? So 60 divided by 3, that gives us 20. Okay. 60 divided by 2, that gives us 30. And then finally 60 divided by 5, that gives us 12. Okay. And then power, right? Remember power. Hopefully you haven't forgotten that formula because we just used it, right? I times V. So 60 times 20 gives us 1200 watts. 30 times 60 gives us 1800 watts. Okay, and then 12 times 60 gives us 720 watts. Okay. Okay. Create an electric potential graph for each of the possible loops. I'm going to skip it because I think it's pretty clear, right? Basically, what you would see for every single one of these is that through the battery it gains 60 volts, and then through the resistor it loses all the volts. So it's actually going to look kind of like a parallel. It's going to look kind of like a trapezoid. You know what? I'm actually going to get roped into drawing it now. So it's going to look something kind of like this. Okay. Right? It's going to look something kind of like this. Okay. And then. Okay, you kind of get the point. It's going to look something like that, okay? Voltmeter and ammeter, right? We're trying to figure out how can we measure the voltage across R3. And remember, voltmeters should always be connected in parallel. So we would, and I don't really have the space because of how my page is folded here, but it would be something like this. Okay. And then the ammeter to measure through R1, you just want to put it in the R1 branch anywhere. I'm just going to put it right here, but you could have put it above it too if you wanted. Okay. All right, example number 3, we have a battery epsilon with internal resistance R and is connected to 2 resistors R1 and R2. Okay, rank the 3 resistors based on which one has the greatest current through it, put equal signs, and you get the point, right? Okay, so first and foremost, right, if our current's leaving the battery, all of it's going through little r. Okay, so the greatest current is of course going to go to of course going to go through little r, so we'll call that I sub little r. Okay, and then so the current is all going to go through the little r, and then it's going to branch off when you get to R1 and R2. And most of it is going to go towards the path of least resistance, right? We've talked about this path of least resistance, okay? So more current's going to go towards 3, and then less is going to go towards 6. So it would be R1, or I guess, sorry, I1. I don't have whiteout at my house, so this is going to be kind of fun, right? And then I'm so sorry if you can see that thing that just said World of Warships just got updated. I'm so sorry. Let me close that. I don't want to play World of Warships right now. Okay. That is so awkward. Okay. In the least current, okay, would have to go to R2 because it has the more resistance in the branch, right? Charges always try and go the path of least resistance. Okay, and then to explain why, right? R is in series and gets all charges. Okay, and then the current must split between R1 and R2, okay, and favors lower resistance. Okay, and favors the lower resistance. Okay, next up, rank the 3 resistors based on which one has the greatest voltage drop across it, right? Okay, so now we're doing based on voltage drop, okay? We know that greater resistance means greater voltage drop, right? If we are, once again, calling upon the pyramid of wisdom. Whoa, what happened there? Did I really, like, mess up my pen or something? Oh, I got some on my fingers. That's crazy. Okay. VIR, okay. I don't know what that was. That was weird. You can see it's on my finger now. Okay. So, V equals IR, right? So the more, so if, so depending on current, right, but also depending on resistance, okay? So we know that, little r has more resistance than R sub 1 and R sub 2, and it's also getting the most current, right? It's more resistance than R1, but less resistance than R2, but it's also getting all of the current, okay? So we can say that I sub R, or sorry, that V sub R is going to be the greatest because it's got more current than R sub 1 and more resistance than R sub 1. And the reason we can say that is because R sub 1 or V sub 1 and V sub 2 should be equal because they're in parallel with each other. Okay, if they're parallel with each other, they have to have the same voltage drop no matter what. Okay. Okay, so to explain it right, R sub 1 is less than little r, so V sub 1 must be less than V sub r, okay? Just by Ohm's law. Okay? And then R sub 1 and R sub 2, same voltage, because they're in parallel. Okay? Ooh, okay. Okay. Because they're in parallel, right? Okay. Now we can actually kind of start filling in the table here, figure out the voltage drop and the current through each resistor, right? Let me just write the notes off to the side, right, and say what's what. So this is R. I think it should actually be little r, okay? Little r is 4 ohms. The R sub 1 is going to be 3 ohms. and then this last one is going to be 6 ohms. And we don't actually really need, I guess we don't really need to write that because we're not trying to find power, okay? And so how this would look is something like this. We could have, well, first off, we need to figure out the current, right? If we can find out the current through the battery, then we can then apply that to figure out the voltage drop on the internal resistance. So to do that, I'm just going to do it. I can do it all in one step. You know, you might not be able to do it all in one step. That's perfectly fine, but I'm just going to do it all in one step, and you may be able to agree with this method. Okay, but equivalent resistance is equal to 1 over 3 plus 1 over 6 to the negative 1 power. Okay, that's our parallel stuff getting resolved into 1, and then we add it to our series resistor. Okay, that should work out, right? Because what we're doing is we're essentially rolling everything into one step. Okay, so we're rolling. This is taking our parallel and getting into 1, and then we're adding it to that. So this will end up with just 1 resistor. Okay, and the equivalent resistance should end up being 6 ohms. Okay, should end up being 6 ohms if you put that into your calculator. Now, when you get 6 ohms, okay, that's the equivalent resistance. We can then figure out the current through the battery, okay, which would be the voltage of the battery, which is 30, okay, and then the resistance is 6, and that gives us a current of 5 amps, okay. And all 5 of those amps are going through the little R here, 5 amps. Okay, we can figure out the voltage drop through through the little R. Okay, by using Ohm's law. 5 times 4 is 20. Okay. Now, here's the fun part, right? We know that at this internal resistance we lose 20 volts, right? But what's next is that the charges are going to either have to go to R1 or R2, and either way that it works, and no matter which way it works out, they have to get rid of all of their energy remaining. So if we initially start with 30 and we lose 20 here, that means 10 volts need to be consumed by each of the resistors on their own. Okay, so that means the voltage drop here should be 10 as well. Okay. Then we can use Ohm's law and get the current, right? Okay, V over R. 10 over 3, that's about 3.3 repeating. Okay, and then 10 divided by 6 is 1.6 repeating. Okay, we don't use a lot of repeating numbers in this class, but we are using it some right now. Okay, and then the potential graphs. So the first 2 segments are going to look the same on both graphs. Then it starts to kind of diverge from that. So the first 2 segments from the battery to the first resistor, it's going to look kind of something like this. And then we drop down. I think it's like, I hate how this graph in particular is set up because it's like there, and then we should lose the rest here. Okay, so it should look something like that. And then again, like this is going to be the exact same thing, especially starting out. Okay. Oh. So it should look, oh actually it should look the same for both, right? Because I keep forgetting, right, the voltage drop on these 2 resistors is the exact same. And then draw a voltmeter that can measure the current across, or sorry, the voltage across R1, and then measure the current across R2. Okay, so if we're trying to find the voltage across R1, we would need to hook it up in parallel to R1. Okay? And then to get the ammeter, or to hook up the ammeter to get the current through R2, we would then need to hook up the ammeter in series just before or just after the resistor. So you can put it right here, or you can put it right here, but it has to be in the branch with the resistor in line with it. Okay? Alright. One more and your suffering is over. Okay. 3 resistors connected to the same ideal voltage source epsilon. Okay. Rank the 3 resistors based on which one has the greatest voltage drop across it. You know, just pretty standard, right? Okay. Well, first off, right, you'll notice that we have two separate parallel branches, and you might be thinking, okay, wait, so the voltage is going to be the same in all of these, right? Because they're all in parallel. Well, not necessarily, because 1 and 3 are not in parallel with each other. Okay, so what's going to happen is if you went through any one loop, you would see that that one loop is from battery to R2 and back. Okay, that means that R2 is having to take 30 volts. There's no ifs, ands, or buts about it. It has to take 30 volts. If the charge decides to go the other way through 1 and 3, then it has to give some volts or some energy to R1 and then some to R3. It doesn't just get to give the same amount to everything. It takes, it'll still be 30, it'll still add up to 30 volts, but now it's having to spread that across two resistors. So we could say that V2 is going to be the absolute greatest no matter what. And then we don't know about 3 and 1, right? Well, we can figure out about 3 and 1, right? Because if we call upon the pyramid of knowledge, sorry, not reckoning, okay, then you'll know that voltage is directly proportional to current and resistance. These two are going to have the same current because they're in series, okay, but their resistances are different. So R3 would then be next, and then V1, okay? And why does it work like this? Well, first off, R2 is parallel to battery. Okay, so if R2 is parallel to the battery, then that means that it has to be giving 30 volts. Okay, and then another thing to point out is that R1 and R3 have same I, but different resistance. Okay. And that's what ultimately gets it. And then you'd use Ohm's law, right? That's just kind of an overview of it. Okay, rank the three resistors based on which one has the greatest current through it. Okay, so now again, we're ranking based on current. So just like we've seen the same song and dance where we were doing voltage, now we're doing current. Okay, rank the three resistors based on the current. Well, we know that 1 and 3 are going to have the same resistance, but we don't know if it's as much as 2. But we can figure that out by taking the equivalent resistance, right, of each branch. We know this is going to be 15. We don't have to prove that. But this series part right up here with R1 and 3, we can turn that into a single resistor. And because they're both in series with each other, we just have to add them. Okay, so the R, I'm going to call this 1,3, is 10 ohms. Okay. Okay, 10 ohms, 15 ohms, okay? The current is going to gravitate more towards the lower resistance, so it's going to gravitate more towards 1 and 3, and 1 and 3 share the same current. So this would be I1, I3, and then by a process of elimination, I2. These two are equal to each other, and then I1 and I3 would be greater than I2, okay? Okay, and just to briefly explain it, right? I1 equals I3, okay, so that takes care of that, and then we know that, I don't know why I said and there, and then we also know that the, REQ of the 1 to 3 branch, okay, we know that is less than the REQ of the, whatever other branch, or of R2 branch. Okay. Okay. Determine the voltage drop and current across through each resistor. Again, this is just another practice in doing that. R1 is 4 ohms, 2 is 15 ohms, and then 3 is 6 ohms. Okay? Okay. Water real quick. Okay. So, so we got all that, right? Okay, we don't know the well, actually, we can immediately get the voltage through R2, right? Because it's in parallel. So we're going to get 30 volts, okay? Okay, 30 volts through that. We can automatically get the current too, right? If we do 30 divided by 15, which is 2 amps, okay? Okay. Oh, I'm so sorry. I felt like there's something I just, okay, whatever. Now, what we can then do, right, is we know that, we know that this is going to, this has 2 amps coming out of it, right? Oh gosh. Okay. So 2 amps are coming out of it. We need to figure out the remaining amount of amps. The easiest way to do this is probably to get the equivalent resistance, right? So if we do REQ equals 1 over 10 plus 1 over 15, we can get the equivalent resistance of that, okay? And that will help us get the current, right? The total current, and we can kind of use some of the Kirchhoff's laws to then solve for the total amount of current. Let me get my calculator out real quickly because I'm going to have to calculate this, okay? And don't mind that stuff that I was writing earlier, okay? Oh, parentheses, 1 over 10 plus 1 over 15, okay? And that goes to the -1 power, and we end up getting 6 as our equivalent resistance for the whole circuit. Because so then we can figure out what the current is, okay, which would just be 30 divided by 6, which would be 5 amps, okay? So if 2 amps went down this branch, that means that 3 amps had to go down the other, okay? And 1 and 3 share those 3 amps, okay? Okay, there you go, right? Okay, now we can figure out the voltage. We're just going to Ohm's law it, right? We're going to do Ohm's law because that's a lot easier, okay? 3 times 4 it gives you 12, and then 3 times 6 gives you 18, okay? And for each of the 2 possible loops, right, for the left one, it's going to be really simple, right? We start out at 30, okay? It's basically just makes a trapezoid, okay? For the other one, again, we start out at 30, okay? And then as we go through R1, we lose 12 volts, okay, to get, we go to 18, okay? So it should be like right about here-ish, okay? Okay. And then we will lose the remaining through R3, okay? A voltmeter that can measure across R3, okay, we would just wire it in parallel. We can start it at A and end it at B if we wanted to. We can draw it however else we want. V, boom. That's the voltmeter across that. And the other question says ammeter that can go across R2. Again, just remember it needs to be in series with this. So you can put the ammeter here if you wanted to, and you could also put it on the right side of the resistor, okay? All right, well, I believe, yep, that is it for solving problems with Kirchhoff's laws. How exciting!